Okay, hello. Welcome to this lecture. I'm going to talk about advanced acceleration methods, specifically the multiband or simultaneous multislice method and compressed sensing, and give you basically a higher level overview of how these two techniques work. First, you can see some really amazing diffusion imaging results actually enabled by these types of acceleration, particularly parallel imaging and the multiband method. So here's the learning goals for this lecture. I'm going to briefly talk about partial Fourier and parallel imaging, although they're covered in detail in prior lectures. So I don't know what the basis for multiband and simultaneous multislice acceleration is, what pulse sequence modification are required, and what sequences are best suited for this method. And then for compressed sensing, well, what is the basis of compressed sensing acceleration and what case-based sampling is used for compressed sensing. So at the end of this lecture, we're going to have covered four types of acceleration methods. The first two we've already talked about, partial Fourier or fractional Necks method, as well as parallel imaging. And then our two new ones, multiband or simultaneous multislice methods and compressed sensing. So just a quick review of fractional Necks or partial Fourier methods, how they ideally work. Here we say if our object we're imaging, little m of xy is real valued, then we have conjugate symmetry in the case-based data. So we only need to cover half of case-base, and we can synthesize the other half of case-base by going to the inverted case-base location and taking the complex conjugate. Now, in practice, this does not actually work very well because the assumption that our object mxy is real valued is hard, but is, I'll call it mostly real valued, meaning it can have some low resolution phase across the image. And so what we do in this case is we do some fractional Necks or partial Fourier where we do some overscanning, cover a little bit of extra of our center region of case-base, so not quite a full half Necks, but maybe sometimes this is referred to as a Necks of how much of case-base we're covering, and it's typically something on the order of maybe 0.6. So we need to cover an extra 10% of case-base to deal with the real-world situation. Okay, but fractional Necks, partial Fourier is a great tool. Then, of course, we also have parallel imaging, where we're going to use our receive coil array to provide some additional localization beyond the magnetic field gradients. And what we're going to be able to do in this is undersample our phase encoded lines, so skip phase encoding lines, which just normally would yield aliased images, but if we could use these techniques like sense or grappa to incorporate the coil sensitivity information, then we can recover unaliased full field of view images and achieve acceleration factors, usually on the order of 2 to 3. Okay, and then one of the new techniques we want to introduce here is multiband or simultaneous multislice. And this addresses an interesting problem. We have a lot of really natively 2D imaging that we like to do, particularly for fMRI, diffusion, 2D fast spin echo sequences. And with the previous techniques we talked about, well, there are ways to accelerate in the imaging direction, so in the two-dimensional plane we're looking at of imaging, but across our slices, none of these previous techniques work. But the solution that this method successfully uses is says, well, instead of acquiring just one slice at a time, what we're going to actually do is accelerate in the slice dimension through the use of a multiband RF pulse. And we're going to excite multiple slices at the same time. So illustrated in the bottom left is a normal sequentially ordered interleaved 2D multi-slice sequence where you go slice 1, slice 2, slice 3, slice 4, and repeat. Slice 1, slice 2, slice 3, slice 4, and so on. Now in these multi-band sequences, we would create a more complex RF pulse where it would excite both slices 1 and 3 together, and then 2 and 4 together, and then back to 1 and 3 and 2 and 4. So this would give a multiband factor of 2 and ultimately an acceleration factor of 2 as well. And okay, so fine, but how do we use this information to actually do the reconstruction? And here I've drawn sort of a simple example where suppose we have this cone-looking object. We're going to image it with two RF coils, coil 1 and coil 2, and our RF pulse is going to excite both this bottom slice and this top slice. Now the key here is that we're going to use the different location, the different coil sensitivities in the slice direction in order to do basically a parallel imaging type reconstruction and recover both of these slices. So nominally, when we excite the slices together, what I've tried to illustrate in these cartoons here is we get an image that's the two slices kind of laid on top of each other. The lower slice in the cone that's smaller, and the larger image from the slice above. But because the coils are different, have different sensitivity profiles across these two slices, the two images are going to look different depending actually on the coil sensitivity profile itself. Okay, so just like the sense method, you can pose this as this kind of unwrapping problem, and we can take these individual coil images that these come from a single scan, right? But they're two slices. We can take this again imaging data from one excitation pulse, add in the coil sensitivity profiles, and formulate this as a parallel imaging reconstruction, and end up then with two slices within only one RF excitation pulse. And this is the basic idea that's really key behind multiband or SMS methods. Okay, so if we can do the reconstruction, that's fine. The other piece we need is we do need to modify the RF pulse. We need to create a multiband RF pulse that's going to excite these multiple slices. And it turns out you can do this in a number of different ways. One, as you could imagine, is you just add up an RF pulse for different slices together. So we just combine the RF waveforms from the different slice excitations, which it could be, we use our Fourier shift theorem to determine what this would be. But there's a couple other variations on that shown here as well. The goal being that for all of these, that they're not just exciting a single slice, but again, multiple slices with a single RF pulse. And there's even some additional tricks you can play with the simultaneous multislice. One of them is to use actually a blipped Z gradient, and we're interestingly actually doing some, looks like sort of a Z on and off phase encoding, and we can analyze this with some case-based and Fourier theory shown here at the right, whereas in this example, the slice 1 that's at isocenter has no change to it from this Blipped Z gradient, but the slice that is off of isocenter gets this oscillating phase pattern every other phase encoding line. And when we have that type of oscillating pattern that occurs every other line in case space, this actually gives us can give us a field of view over 2 shift in our reconstructed image. Okay, so our slice 1 is going to end up being shown in the center of our image, and our slice 2, because of this Z gradient and it's at a different Z location, is going to be shifted off by a field of view over 2. So this method is sometimes called Caipirinha, and the middle row illustrates how we might do that, where we could do, so this is multiband 4 exciting 4 different slices, and we can see in the resulting image we get these field of view over 2 shifts for some of our slices, and we can even do field of view over 4 shifts and shift all 4 of these slices into slightly different locations on the resulting images. And this is actually going to make it easier, as you can see visually. It's already just visually easier to separate, realize that you have different slices here, and that visual intuition is going to extend into the parallel imaging reconstruction improvement, and which we see in the G factor maps here. So normally without this blip sampling, this Caipirinha, we might get actually pretty large G factor maps under this scenario here, where the left image just shows how the 2 slices overlap onto each other. We have a lot of noise amplification. You can see in the slice 1 and slice 2 images, they're pretty noisy. But now when we add this Caipirinha shift, so shift the field of view of one of the slices by 2, then actually the reconstruction problem, which is also actually a sense reconstruction, to do the multiband reconstruction, that our G factor map is basically 1, meaning we're not adding any sort of parallel imaging or G factor penalty by doing the multiband excitation with this blip sampling. And just some more nice looking results. This technique has been very successfully applied, and there's even this newer technique called wave Caipi, and anyway, this is here for your viewing enjoyment and reference if you're interested to learn more. Okay, and finally, I want to cover the compressed sensing acceleration technique, which has also now become common on commercial MRI systems for accelerating MRI scans. And the idea here is that there's some sparse way to represent our data or our images. And compressed sensing is not a specific term to MRI. It's a general term coming actually from mostly the statistical literature that says, well, we can actually recover the we can undersample our data, but if we have this knowledge that our data is sparse in some domain, we can actually, recover our fully sampled data with this model. And in In fact, MRI data is actually quite sparse. Our sort of typical images are sparse, or you can think of them as compressible with something called like a wavelet transform, which is illustrated in the top middle plot at the right there. Something like an angiogram is just a lot of individual bright spots, so that's can be sparsely represented by this like a finite difference map, meaning when we take the image, we transform with finite differences. We can see there's a fewer number of bright pixels in this image. Or dynamic imaging as well. You can see if we have a repetitive motion, then that, if we take the Fourier transform of that repetitive motion, then we see, well, that's actually really compresses the image or compresses the signal. Again, we see just a lot fewer bright pixels in the image, meaning that it's been well compressed. So that's what this first requirement is referring to, is that we need data sparsity in some domain. Wavelet is a very common one, finite differences as well. And this turns out to be true for most all MRIs. Then we have a second requirement of creating incoherent aliasing in the transform domain. I'll go through that in a minute. Kind of similar to parallel imaging, we do need sufficient SNR. So we are going to do, we're going to try to require less data, which is going to fundamentally lead to reduced total measurement time, which reduces the total SNR. And then we need to go through some nonlinear image reconstruction. So not simply just the FFT, but we do need to take into account this data sparsity in typically an iterative reconstruction. Okay, so here is a conceptual illustration of what happens in compressed sensing. So you can imagine maybe we have a sparse image, just consists of 3 locations. Our signal is determined by the Fourier transform would look like so. And what can happen if we just undersample the signal at regular intervals, like we've looked at, for example, in parallel imaging, is that we're going to get this actually this coherent aliasing, meaning there's some ambiguity here in this bottom plot, number D. Not number, letter D, whereby we can't tell which are the real, when we have the aliasing, like which is the real sample here, and we can even see this drawing is done to purposely have the orange and the blue signals overlapping on top of each other, making them impossible to distinguish. So what we do instead is illustrated by the red dots on the top of part B here, which is this pseudo-random sampling. So we kind of pick these points at random. And it turns out this, when this occurs, the aliasing from this pseudo-random sampling, this artifact, aliasing artifact, in fact, starts to look like noise. Okay, so actually the signal you would reconstruct from this set of pseudo-random measurements would look something like part C here. Okay, so that's a start, right? We can see we've got a couple of the signals there. We do still have a bunch of aliasing artifacts. So what we do is we apply this sparsity model and we say, well, let's extract just the sparse signals that we can find so far. Okay, and then assume there are sparse in this case in their native domain. So we say, okay, we've just got these points, these sparse signals in this domain. Now we know our sampling, our pseudo-random sampling pattern, so we can actually compute the aliasing artifact generated by these 2 points. And that's what's shown in part H here. And so we can actually subtract off this, what looks like noise, but it's actually aliasing. We can subtract off this aliasing from our original signal. And then if we've got our sparsity model right, we calculated our aliasing from the pseudo-random sampling, this noise-like aliasing, we should be able to get to a situation where now we can actually see this smaller coefficient, this blue peak, because we've removed the other peaks and also their the pseudo-random aliasing contribution, this artifacts to reveal the smaller signals. And this is an example of a specific algorithm called iterative soft thresholding. In practice, we typically use other algorithms and maybe more complex sparse representations of the data. But this gives you the concept of why we need to do this pseudo-random undersampling. We need to make our undersampling artifacts look like noise. And we can extend this from this 1D example to 2D multislice or 3D imaging. And here, that you can see illustrated in this 3D Cartesian sampling pattern, is that you have 2 dimensions of phase encoding, but there's pseudo-random undersampling in these 2 dimensions of phase encoding. And then we have a reference Nyquist sampling reconstruction here. If we just do low resolution, obviously the images look blurry, don't look great. If we try to just take our pseudo-random undersampled measurements and do a linear reconstruction on them, we see we're starting to see structure, but we can tell it's really not quite right. We're missing the boundary. We see a lot of residual incoherent aliasing artifacts. And then if we go to the compressed sensing or CS reconstruction, we can see that we have really nice fidelity of our reconstructed images. And similarly shown in the brain example at the bottom, when we apply compressed sensing reconstruction with both a wavelet and total variation, sparsifying transform, we can get a really nice high quality reconstruction of our original image, but with a fraction of the data being acquired. Okay. Sort of an aside here, the wavelet transform that I'm showing here, this is actually also the basis of a lot of JPEG image compression for natural images. Turns out MRIs share a lot of properties with natural images and can also be highly compressed with this wavelet transform. Okay, so about to wrap up here. Here's a comparison of our acceleration methods. We have partial Fourier, where the main trick is we need to estimate or measure some phase because the images are not perfectly real, but it's very broadly applicable. We have parallel imaging, where we need to then have our RF coil arrays. It has the advantages of it's very simple understanding. We can apply with most pulse sequences. But we do need to be aware of the coil geometry and the G factor, which influences where we can do our acceleration. Then introduced here are the multiband or SMS methods. We need to add these special tailored RF pulses, and it's going to be applied to 2D or multi-slice methods. And it adds the ability in these 2D methods to actually accelerate with a low G factor in the slice dimension, particularly when using the blipped Caipirinha sampling. But the cons are sort of this increased demand on the RF pulses. And then finally introduce compressed sensing, where the requirements are that we have a sparse signal representation, which turns out to be basically always true, SNR, and then implement some pseudo-random sampling. It's very general, can apply in a large number of circumstances. We can actually combine this with like partial Fourier, with parallel imaging. The cons are a little bit subtle, at least in my opinion, are these sort of nonlinear reconstruction artifacts, which don't necessarily appear as like strong aliasing edges. They're a little bit harder to pick out visually, sort of maybe a more subtle smoothing of the signal. So there's that potential for a failure mode of the compressed sensing reconstructions. Okay, and with that, we've come to the end of this lecture, so hopefully got a flavor for all of these different learning goals shown here. Thank you very much.